Hi, in this video we're going to take a quick break from the mirrors and ray diagrams and go back to the concept of the speed of light. Remember, the speed of light can travel through a vacuum or space, and it can also travel through water or glass or air, and that's called index of refraction, which is something slower. So speed of light in a vacuum travels very fast. Right, so the speed of light in a vacuum is 3 times 10 to the 8 meters per second. And we give that a special symbol called the letter C. It's a small c. The index of refraction is a ratio of these two speeds. So essentially what this is n is equal to c divided by v. So c in this case is 3 times 10 to the 8 because it's the speed of light in a vacuum. And v is essentially the speed of light in water or in a different substance. So speed of light in water or air or a different substance, like diamond, for example, substance. Okay, so any substance, and that will give you the index of refraction. And there's a whole bunch of lists online that you could look up. Like, for example, air is water is 1.33. All right, diamond is 2.42. There's different values. And essentially what that is that water really slows down light, but so does diamond. In fact, diamond slows it down a lot, all right, because this here is your maximum value. This is as fast as it's going to go. It can't go any faster. And this here is going to be generally slower, so it makes this divided by that, which is n, anything larger than 1, pretty much, okay? And so generally this here is slow, very slow. This here is at max speed. Can't go any faster. All right. And then this here, n, is going to be always more than 1. 1 or more. More than 1. Because usually we don't say the index of refraction of a vacuum because that's just, well, the speed of light. All right. Okay, so how do I know that light slows down? Well, what happens is that the light does bend, and I'm going to show you a couple of cool things here. The first one I'm going to show you is a semicircle, all right? And I'm going to show you that light does bend because when I shoot the light in, it will bend one way or another. Hello, all right. Finally, I set up a dark room and everything works quite nicely, so this is good. This here is called a ray box. I'm going to do some cool demos. Um, and this here are slits. And so instead of big long beam like this, I'm going to just put it to one single slit like this for you to see. Now, I want to prove to you that light does indeed bend in plastic. Plastic is typically 1.5, which is slower, yes. And so you'll notice here, the light goes straight through, and you know it goes straight through because, the ruler tells you it's nice and straight. Um, However, if the light approaches a boundary, this is a boundary, and right now it's perpendicular, all right? So the light makes a 90 degrees to this boundary right there. But let's say if it goes off on an angle, okay? You will notice that the light does bend now. Okay, so now the light, if it was to go straight through, here's my ruler, it would have gone this path. But because now it's gone, here, let's just make sure it's straight, I would have gone that straight path. And I'll just make it bendy even more so you can see. So you'll notice it bends. It should go straight through if it didn't slow down the light, okay? But what's happening is the light hits the plastic, it slows down, and it bends the light. And as it exits, it continues again at speed of light in a vacuum. All right, so there is bending going on, and that's how we know that plastics, diamond, water slows down the speed of light, which is kind of neat, all right, because it has this bendy type property. you can actually calculate how much this light bends. And that is using Snell's law to calculate that. And that will be the next lesson. So I will see you next time. Bye now.